Now we have Renate Loll from Radboud University, who's going to tell us about quantum Ricci curvature and quantum gravity.
Okay. Do we have this running commentary?
Shane, can you remove the?
One second to turn that off.
Okay. Can we go full screen?
You need to turn this off.
Okay. So, but this is still there. Okay. You turn this on, and that won't have the.
And then I'll have full control.
There's a method that's being enabled.
It's not visible yet. Okay, we are ready to go?
Looks like it.
Oops. Okay.
Yep.
All right, here we go. So thank you for the patience, and thanks, of course, to the organizers for their brave attempt to bring together mathematicians and some physicists in the hope to generate some mutual understanding. So I hope to pitch my talk in a way where at least I try and point to issues that might be of mutual interest. Okay, so this will be about curvature. Curvature is, of course, a wonderful, but I would say exceedingly complex notion in anything beyond, say, dimension 2. I will look at curvature in the context of quantum gravity. So before I get to curvature, I'll have to give you some motivation of why I'm looking at this and what I'm looking for when asking about curvature. So here is my perspective of where I'm coming from talking about non-smooth geometry. So I'm trying to construct a fundamental theory of quantum gravity. So as a non-perturbative, diffeomorphism invariant quantum field theory. So let the buzzwords just, drift by of dynamical geometry. So the dynamical is important, and we know that comes with a host of difficulties of all kinds. So for the purposes of today, however, I will not focus really on the quantum field theory. So there are, of course, there's lots to talk about, but I'll highlight more the kind of the geometric and quantum geometric aspects. So, and one of the key questions for us, also here for the purposes of this audience, so what becomes of the classical notion of space-time once we go to a very highly quantum fluctuating, very short distance regime? So that's typically identified as with a Planck scale here, L Planck, that I introduce here. And so that motivates a lot of why I'm interested in going beyond classical geometry. So some of the key take-home messages of my talk will be, firstly, applying methods from so-called random geometry, which I'll explain a little further, in a physical context where we need things to be four-dimensional and of Lorentzian signature, has been very fruitful. And the particular approach I've been following to implement this is called CDT, or Causal Dynamical Triangulations, and I'll, of course, introduce this in more detail later on in my talk. Now, what is very important in any approach to quantum gravity that should be fundamental is, according to what I would say, identifying and studying certain observables. So if there is a quantum space-time, how do we describe it? What kind of properties can it have? So it's just, of course, there's an analog of classical observables. And one particular one interesting for today will be the quantum, what I call quantum Ricci curvature. So among the applications and motivations for constructing and implementing this notion of curvature on quantum space-time is to analyze an emergent quantum universe that's generated in this particular candidate theory of quantum gravity, and to understand it better, to understand what its curvature properties are. And that again poses, of course, challenges when you are in a regime where you are very far, you cannot even use tensor calculus. Okay, so what does it even mean? So here I take the opportunity to advertise a recent kind of overview and review I've written on quantum gravity. So if you want to delve more into the motivation and history of over the last 20 years of what's behind really my story today. Okay, so quantum gravity will define for today's purposes as going beyond classical geometry. There's of course not a unique way of doing it, but we are after certain things in quantum gravity. So somewhat illustrated by this picture here on the left. Now, so the idea is we are starting from a kind of a piece of empty, let's not consider matter for the moment, just empty space-time, yeah, like whatever, pump out all the atoms from here and we'll be in a essentially empty piece of space-time. But zoom in on that, go to, I mean, put it under an imaginary microscope. So what will we see as we crank up our resolution? So we will start maybe seeing some kind of gentle kind of curvature fluctuation. And once we get to this mysterious Planck scale, which is on the order of 10 to the minus 34 minus 35 meters, then, well, we expect that quantum fluctuations of space-time itself will kind of completely take over. This is, of course, and so then people draw, you know, quantum foams or quantum space-times. It's all, of course, totally hand-waving. Yeah. So the question one could ask here, are there genuine models that allow me to say anything about this regime in a quantitative way without just drawing fancy pictures, and what's the right way to approach this? So I'm, of course, cutting a long story very short, but so the way to think about this is as follows. We are, of course, not just after quantum space-time. I mean, people like myself, we are after a theory of quantum gravity, which is, of course, dynamics of certain degrees of freedom, which, roughly speaking, are geometric. So let us assume there is some kind of geometric remnant. So classically, of course, we would, what's a classical space-time? Well, it's not something that's given to you, but you have to work for it by solving Einstein's equations, subject to boundary conditions, symmetry assumptions. Okay, so similarly, you should think of quantum space-time as something that you have to work for. You cannot just put out there and postulate. It should come out as, you know, maybe a ground state of some quantum dynamical system of certain, you know, local degrees of freedom that presumably somehow know about geometry, for if you want to take a quite conservative attitude. So such a prescription, of course, must account for these quantum fluctuations that appear in this picture here. So why is this kind of difficult from a quantum field theoretic point of view? If I can just briefly mention this, there is no, unlike when you're looking at, say, gauge theories, yeah, where you assume a fixed space-time background, typically flat. This here doesn't have any a priori given background. So you have to, whatever machinery you have to produce a quantum theory for you, somehow it has to take that into account, that there is nothing a priori. That also means, so there's no a priori metric. You have to work for it to get it. That also means you don't have a natural scale floating around. So you don't a priori know this is 1 meter, and, you know, on the contrary, quantum geometry, of course, will set a scale, for instance, by something like curvature. Okay, so how do you go about this? We know already that perturbatively, you run into big trouble if you start, you know, thinking of G mu nu as Minkowski plus little quantum wiggle. So that doesn't lead to a fundamental theory. So we have to go non-perturbative. And I'm mentioning here, so my own approach is CDT, but also something like the causal sets that Faye Dowker talked about yesterday are different approaches that really go very much beyond this kind of perturbative idea and allow you, so what does mean non-perturbative, allow you in principle to address large quantum fluctuation on short distance. So things are nowhere near smooth. So this cannot be, you are in a regime where this cannot possibly be described by nice solutions, the Einstein equations plus little perturbations around it. So how do we go about this? So there are various ways of doing this. So they often employ or postulate, non-smooth metric structures, where the spacetimes themselves may or may not be discrete. Now, if you model spacetime just by a set or so, then of course you're in a discrete setting, but what I'll be talking about will always be continuous. And it will be, in my case, it will be piecewise flat or obtained by certain limits of piecewise flat objects. So again, is this just hand waving or can we calculate anything? And interesting, so what of classical geometry will survive? Yeah, or of course, conversely, if you give me your wild Planckian model, what can be retrieved in a suitable limit? So, if you have a Planckian model, yeah, one thing you certainly have to test is that if you go to suitably large distances, it should reproduce something we recognize from Einstein's theory, because that's a good theory on large kind of classical scales. And that's a very difficult boundary condition to satisfy for generic quantum gravity theories. Now, quantum observables, as I have already said, will be very important for us in the story. So now let me go to the specifics of the approach that I'm using to address these issues. So that was the story of dynamical triangulations, or my variant is that of causal, having a causal structure present, which turns out to be a very important ingredient. So what is really behind it? From a kind of physics point of view, what's the dynamical principle that I'm implementing, even I believe in on the Planck scale, it's really the superposition principle. That means, I have, the fundamental principle of quantum theory, where what we're calling a path integral, I'm summing over amplitudes kind of all possible configurations my system can have. And here, a possible configuration is a possible kind of curvature, curved space-time. So I want to superpose those and in a, what's written as a formal path integral. Yeah, so this is an integral over all. I'm given some topological, a space-time M, topological space M. The differentiable manifold could be something more general. Here it's just, classical, using classical language. I look at all Lorentzian metrics on those modulo diffeomorphisms, and these are my geometries. And I'm instructed to put them in a big superposition principle. Each one I weigh with e to the I, so a complex amplitude, where the S here is some version of the gravitational action, so Einstein action, or with a cosmological constant term typically. Okay, so this is something we want to implement, but of course it's a very formal thing, and dynamical triangulation is one way to make this a precise prescription. And what the CDT does, it actually builds on the previous version of where people have used a way to implement such a partition function, or rather a superposition, where they, for reasons of simplicity, have used Riemannian spacetimes in the superposition, and at the same time kind of substituted the complex amplitudes by real weights, e to the minus s. So s is always a real quantity. So that's what people did, starting in the 80s, actually a development coming from string theory. Yes, you have a question?
Yes, in Lorentzian of M, do you only include real coefficients?
No, it's all real. Here, these are both real actions.
And so
Yeah.
Is the Hilbert action, or
It's typically in our examples, it will all be, it's flashed, it comes on the next slide. It's the Einstein-Hilbert action with a cosmological term, precisely. It could be something more general, if you fancy it. So what is here? How do we make sense of that? We are appealing to a simpler way to talk about curved spaces and space-times by employing what, as a physicist, I would call a regularization. But let me tell you what it is in a simple case where we, let's say, choose Riemannian signature, choose 2 dimensions just to have a toy model of what's going on. So you are given n equilateral triangles, and your task is to glue them together to give, let's say, something that's topologically a sphere, by running through all inequivalent ways of gluing them together. You stick them into this Euclidean version of the superposition, and you try to do this computation. So that will be actually very simple. Here, the S will be just the volume of your 2-dimensional thing. And that this can be done, and is actually a beautiful thing that links to a hot topic in mathematics, which is called random geometry. And it's really based on 2-dimensional, the idea of taking now a limit of this expression as you take the number of building blocks n to infinity. So on what you then obtain is a kind of a quantum geometry, one could call it. People call it, one instance is the so-called Brownian sphere. And the Brownian sphere is really two-dimensional random surfaces, what Brownian motion is to 1-dimensional random path. So this is the way to think about it. And there's, I recommend this VVRT-Sheffield. So it's a huge universe, but it started in physics by trying to understand worldsheet dynamics of strings, or later on quantum gravity systems. So, however, what we are interested in are higher dimensions. So 2D, I'm not a string theorist, so I'm not so much interested in worldsheets. I want to understand 4-dimensional curved spacetimes. Okay. So, and well, I'm not interested in them being Riemannian, but mine, they have flight cones. So there's a Lorentzian structure. Is it possible to say something about this case? And it turns out it's not only possible, but if you're interested in higher dimensional generalization, then this, what we call Euclidean or Riemannian version, doesn't seem to give any interesting results. It's a very long story, but if already, say, in these 2-dimensional toy models, instead of using kind of Euclidean equilateral building blocks, you use Minkowskian building blocks, but otherwise, the rules are the same. You're going back to this here, you regularize it, the set of all geometries, by the set of all gluings, where you glue this elementary building block in all possible ways, such that you get a causally well-behaved 2-dimensional random geometry. Then in 2 dimensions, this gives an inequivalent model to the purely Euclidean one. So that's nice. In higher dimensions, it gives something interesting, where this Euclidean Riemannian version only gave you degenerate stories and no interesting extended geometry. Nothing interesting ever emerged, to use this somewhat loaded term. Okay, so here we are, and that was the beginning of the CDT approach. So, yeah, you had a question. Yes.
Could the theory accommodate a relation between a Euclidean path integral and a Lorentzian one, as in the boundary integral, or?
Well, it's really a different ball game. So maybe it will become clear what I say now more about how anyway, how I wick rotate, because I need to wick rotate. So maybe, remember your question. Oops, what's missing there? Something's missing there. Okay, so here is my path integral. So you asked about the action before. So this is a formal continuum thing. Please contact the person who created the PDF document. Yeah, that's me. Now, what was there? How bizarre. Okay. So this is the object we are trying to implement. It's a very formal thing. I mean, in the continuum, it doesn't really exist. So the way, the concrete thing one does in the CDT version is one transforms it into a sum over inequivalent causal triangulation of n building blocks with a simple weight here. This is kind of the CT is the the size of the automorphism group of the triangulation T, the causal triangulation T, and you weigh it with a simplicial version of the Einstein-Hilbert action, which is here. Oh, that stands for Regi or regularized. So it comes from Regi calculus, but of course, what we are doing here, we are working with essentially with equilateral building blocks, whereas in Regi calculus you're allowed to, to change the edge length. So here, what we are doing, we are fixing the edge length and allow arbitrary gluings, whereas in Regi calculus you do the opposite thing. You fix a lattice and then you allow modulo triangle inequalities, the edge lengths to vary. So we are doing something complementary, which turns out to be, more suitable to explore this very non-perturbative regime. So what you should think of this thing as, well, there are too many technical details. Just a black box that generates a quantum geometry whose properties I'm now going to explore and telling you how to do it. But a number of remarks are in order for you to appreciate, some of the rules that go into this. So we are not per se interested in finite triangulation. So keep where the n is finite, but really only what we call the continuum limit. And why is this? Well, to ensure that I've regularized, I've postulated my spacetime to be made up of little triangles. You may come with squares or pentagons or something else. That shouldn't matter. That's this part of what we call the regularization. So let's make sure that we're taking a limit where most of these unimportant choices drop out and don't affect the final result. So that's one way of doing it. So what we're also doing, so n is the number of building blocks. So typically the limit is taken by keeping kind of what we call a physical volume finite, physical in a dimensionful volume V. And so n is just a number of building blocks, and A is kind of a unit of length, the lattice spacing. So you can equivalently think of this limit as n going to infinity, or also sometimes A going to 0. But the idea is the same. I have a finite chunk of space-time, and I subdivide it with my triangles in a finer and finer and finer way. And I look only for interesting behaviors that I see in the limit, in the continuum limit. And I may have to rescale and renormalize my constants, etc. It's a longer story, but that's the rule of the game. So what about the C of the causal? So the individual, what is happening here is that the individual objects that enter into here are required to obey kind of a discrete version of global hyperbolicity. So that's realized in the way I'm sketching here. Basically, you have kind of slices of constant integer time, which we loosely think of as a proper time, and you're building in between. This is now in 3 dimensions for simplicity. Your simplices or your triangular building blocks, they extrapolate from one slice to the next. This looks like a very orderly picture, so that is slightly misleading because the slices here will be completely wild and random and very curved. And so this picture is just schematic to tell you what's going on. And we use the same story in 4 dimensions. So you have 3-dimensional kind of equilateral slices of spatial geometry, and then you interpolate kind of with 4-dimensional building blocks, and the one elementary building block is shown here in 4-dimensional CDT, and you just build up your spacetimes. And so so what's here? So what we have to do, we cannot, beyond 2 dimensions, we cannot evaluate this analytically. In 2D we can, and that's an important sanity check that this methodology is kind of valid. So in higher dimensions, we can only explore this with numerical methods. And in order to do this, to use Monte Carlo simulations, we have to get rid of the complexity of these amplitudes. And this is what we achieve by an analytic continuation, which exists on these piecewise flat objects that I'm using as my configurations. So this is something that is not known to exist in the continuum. There is no immediate analog of this. So it's interesting. How does it work? Well, you had on the previous slide, you saw I had edge lengths that are time-like and edge lengths that are space-like, so which are in red and blue respectively. So the time-like ones, I can just parameterize them as some multiple of the space-like ones, because everything is, as close to equilateral as possible. We are in Lorentzian space though. So alpha, if I'm Lorentzian, is a positive number. So what now constitutes my Wick rotation is to rotate this alpha in the complex alpha plane. This is what you have to do. It turns out to minus alpha. And then you will see that all your edges become space-like. And if you analyze how this affects the Einstein action, you will see that the alpha dependence, when rotated in this way, maps exactly the Lorentzian Einstein action to the Riemannian Einstein action. So that's beautiful, and that we need because the computations are done in Riemannian signature, because for technical reasons. And of course, then we have, after the computation, of course, we have to explain how we rotate it back and how we Lorentzian interpret this. Someone yesterday said, how do we Lorentzify this? Yes.
So I'm puzzled that you said in 2D you can compute this thing, but the Einstein action did not work in 2D, right?
No, the Einstein. Well, it doesn't work in the sense, of course, there is no interesting theory of gravity because, as you're saying, so there is only a volume term. So in 2 dimensions, this here, just only the volume term is left over. But you see, it's an interesting toy model that people also in the continuums, have, like in Liouville gravity, have studied endlessly. And it's a beautiful toy model. There is no classical limit because there is no non-trivial Einstein gravity in 2 dimensions, but nevertheless, it's a beautiful illustrative model. It's, if you like, pure quantum, but it's very, very non-trivial. So it's a long story in itself. So what was here was a drawing of an equilateral triangulation in 2D of regular triangles meeting around a vertex to illustrate the notion of the deficit angle. So how do these gluings of simple equilateral building blocks, how do they know about curvature? Well, through deficit angles. So if I put 6 around the vertex, 6 equilateral ones in 2 dimensions in a Euclidean context, there I get a piece of flat spacetime. When I remove one of the triangles, I get something that has a local curvature, has a deficit angle which is equal to the Gaussian curvature in a direct way. And the same principle, and this is kind of due to Radboud and Ricci calculus, works in higher dimensions. Yeah. Now, what is not true is that this notion of curvature stays meaningful in the limit as n going to infinity. That will require me exactly to do something different and do my quantum Ricci curvature. So I hope there's not more missing on my remaining slides. But here we go. So now let's jump to results because that's where the geometry will come in. So I have a computational framework. So what can I do with it? Well, I said before, I have to look at certain observables. Now in gravity, also different, because I don't have an a priori given background in a way. And for the time being, I look only at pure gravity. So I don't put any matter in. It turns out that the quantum observables I have are very non-local objects. Yeah. So here, generally speaking, I average, so the way I'm now already in my Wick rotated, if you like, Riemannian framework. So what I do, I had the Z before, this is a normalization factor. So O is just some function of the metric degrees of freedom. Yeah? And I evaluate kind of its average with the weights e to the minus s in this ensemble I've chosen. Yeah? And of course, I have to do that in the end in the limit as n goes to infinity. But that's kind of the simple recipe. What can I use for O here? Well, it has to be, of course, invariant diffeomorphism, invariant quantities. So for the purpose here, I don't have any matter. I don't have any way to point at what I mean by the point x. What I have to do in order to get to a diffeomorphism invariant observable is to, for instance, the simplest way is to integrate a scalar over all space-time. Okay, so, and here, I don't know why, there is now a piece missing, which is just integrates the Ricci scalar over M. So that's a typical non-local observable that satisfies all my criteria here. Okay, so the Ricci curvature, even a scalar quantity at the point x, is nothing that's of use to me in this type of superposition game, because there are many members in the ensemble I have to average over, And there is no way to say, oh, the point X in this geometry, I identify with this other point X in the next geometry. So that already also tells you that this is not a sensible statement. It makes, so the non-local nature of these observables is of course a little bit special and doesn't relate in an easy way to typical questions we ask, even if you're working on classical GR or its properties. So we often think of specific solutions, and we are often thinking implicitly of coordinate systems that allow us to say where something is, right? I'm just saying here in this game, you don't have that luxury. Certainly not if you don't put any matter in, which could say, oh, the point where whatever the scalar field has the value 37, that marks for me is a certain point X. So that's not what I'm doing, but nevertheless, it's an interesting and non-trivial ball game. Okay, so is there an interesting observable I can point to, which is kind of purely quantum and which makes, has a true quantum signature, which is unexpected from a classical point of view? Yes, there's a single thing I can point you to, and that was first predicted in the framework of CDT. When you study the so-called spectral dimension of now the quantum space-time, the spectral dimension is an effective dimension seen by a diffusion process or random walker, if you like. Yeah? So this is a well-defined concept on very, very general types of spaces, including the quantum space I'm working with here. And when we investigated this first, we saw that when we looked at the spectral dimension for long random walks, which probe kind of large-scale classical regimes, the spectral dimension is compatible with the value 4, as one would hope, when this has a good classical limit. However, when we approach the Planck scale, then the curve dipped down to somewhere in the vicinity of 2 with large error bars. So we call this dimensional reduction. And it's a phenomenon that has been investigated since in many other approaches, and people finding similar results to the extent it has been hypothesized, for example, by Khalib, that this is a universal feature or quantum signature of quantum gravity. Okay, so that's one definitely a quantum feature which is unexpected and is non-classical. You cannot explain, right? A Riemannian space whose dimension, when you go to small scales, kind of dips from 4 towards 2. Now, it's a general feature of this random geometric systems, and it was already known in 2 dimensions. So people who studied 2-dimensional Euclidean quantum gravity or Liouville gravity, they found that the Hausdorff dimension, so you can there analytically compute these things, is 4. And the spectral dimension in this case is 2. But generically, because you're taking a non-trivial infinite limit here, typically the topological dimension of the microscopic building blocks does not predetermine those notions of dimension. And of course, that's interesting. So that's interesting physics potentially when you find these phenomena in higher dimensions. My goodness. Okay, more is missing here. Interesting. So we have emergence of classicality. Emergence is a loaded notion, and emergence in a very specific sense of you have a microscopic system of microscopic building blocks. You look at their joint dynamics and outcomes. If you look at the macroscopic system that ensues, it has new properties that you couldn't predict just from looking at the microscopic one. So that's what this is kind of emergence in the statistical mechanics thing. And what happens here is that indeed there's a missing plot here, which shows you that quantum geometries that come out of the CDT quantum gravity. So if you look at one of the observables there, which is the 3-dimensional volume as a function of proper time, if you plot its expectation value as a function of time, it has a beautiful curve that can be mapped onto a cosine cubed. So that's a missing, that's terrible, the missing graph here. And so it's very suggestive. So how does the theory know about this? We don't know. It's a collective effect of these microscopic degrees of freedom, and you don't see it if you start in a Euclidean Riemannian universe to start with. So here in this causal dynamical game, you this seems what happens. So does that allow me, just having looked at the global shape and having mapped this to great accuracy to that of a de Sitter space around S4 in Euclidean signature, does it allow me to conclude that my quantum universe in some suitable large-scale limit is just described kind of by the de Sitter line element? Well, it's a rhetorical question. It does not, because I'm just picking out one very global mode of the metric, and the rest is presumably still very quantum fluctuating. So for a long time, the question was, well, how can we gather more evidence? What is this? And of course, one thing you really would like to look at is curvature, right? An S4 is a constantly curved space. So is there any way in which you can say that our wild quantum geometries are constantly curved, maybe on sufficiently large scales? And that brings in the question for a notion, a well-defined notion of curvature that can be implemented in this Planckian regime. And it's really the question to say, well, is it meaningful? Can I associate in a kind of quasi-local sense a notion of curvature to a highly non-smooth object, like a typical kind of quantum geometry that comes out of this game? Yeah. Yes. Yeah, so this is a proper time form, but you see, it's of course a Riemannian signature. So there is no, because I have rotated to Riemannian signature, yeah, there is no minus dt squared. So, exactly. And indeed, you see, since, I mean, our T has a proper time interpretation because of this matching, one would say, now this is now very suggestive of kind of rotating back and interpreting this as really a Euclidean Riemannian expression of the system really wanting to be a Lorentzian de Sitter space. Okay, so that's the logic. So here we come to quantum Ricci curvature. So the beautiful idea, which is heavily inspired by Olivier's idea of what people call now the Olivier-Ricci curvature, is needs very little in terms of ingredients. So it works on very general metric spaces, and that's something I'll be adapting to the present context. So what is the key idea? In d dimensions, we compare the distance between two d-1 spheres for some definition of notion of distance between extended spaces. Here it's a drawing in 2D with the distance delta between their centers. So in 2D, let's just think of a smooth Riemannian context. We are taking a p and a p prime at geodesic distance delta. We draw two epsilon spheres around those, and we compute d over bar, the distance between those two spheres, and compare it with delta. So the point is that.
Sorry, your picture makes it clear what delta is, but I don't see what d bar is.
D bar, yeah, I get to it here. So it's the distance between the two spheres, which I have to define in some way for you as point sets, okay? So on a metric, but this holds independent almost of what precise choice I make. On a metric space with positive Ricci curvature, the distance d bar of these two spheres will be smaller than the distance of the centers. And you can kind of, if you're thinking, putting yourself on a 2D surface, you can kind of have a little intuition for that. And conversely, if the Ricci curvature is negative, then the distance between those two spheres is bigger than the distance between the centers. So how do we use it? I mean, Olivier and people who have applied this, they're using transport distance. They're using optimal transport distance. This is very, for us, this is very, very expensive computationally, because you have to find the optimal transport from every little bit of that sphere to every little bit of that other sphere. And we're interested in macroscopically sized spheres, so this just doesn't work. But what turns out to work is really, for our purposes, is equivalent, I would say, is to just use the average sphere distance, where we're simply averaging over all pairs of points. So that's still expensive, but not quite as crazily expensive. So here, that's what it is. You know, we are just integrating over pairs of points, and the distance is given this. So I need a notion of distance, dg, between pairs of points. And what we are also doing in order to have this whole thing just depend on the single scale is we are just choosing epsilon, the radius of the spheres, equal to the distance between the two centers. You could make other choices, but this is what we are doing. And we are because we are interested in dependence on delta. My God, there's a formula missing. This is just terrible. I should have checked this beforehand. Now, so the beauty is, well, there are many aspects to the beauty of this prescription. So what I'm doing now, this missing formula is, let me go back, is we're taking the quotient of the sphere distance here, d bar, and the delta. So the interesting thing, and what makes this what I would call robust, is these are they're two quantities of the same type. So they are distances in your non-classical space. So robustness is typically the scaling of these different quantities, volumes, areas, lengths. They can be very non-canonical and very non-classical, but it makes things, I'm now taking a quotient of two distances that increases the likelihood that this is somewhat robust under non-canonical scaling relations that do, as I said, they do typically occur in these random geometries. Okay, so here, what's written here is d bar divided by delta equal to CQ, open bracket, 1 minus KQ, bracket closed. So we are lumping together everything into kind of a constant piece, which depends on what turns out to be a non-universal constant, depending both on the type and the dimension of the space, and kind of a correction term, which is kind of the, you know, if you're going now to a continuum, is kind of the delta squared corrections, which know about curvature. And this is really kind of taken from the playbook of Olivier. So if you evaluate this on a Riemannian manifold, this quotient, that's what you find in dimension 2, 3, and 4. It's a beautiful and painful computation in Riemann normal coordinates. And you see, you get a constant here, which turns out to be dimension dependent, but otherwise universal. And then you find at order delta squared, you find exactly Ricci and scalar curvature. Okay. But this is, of course, not the context we are interested in. We are interested in applying this to much more general geometries, where we can measure volumes, so we have some kind of measure, and we can measure geodesic distances. And that's true for my quantum geometry. Okay. The beauty is, you know, it's kind of so the poor woman's implementation of a vector, which is this vector v here, right, which is just, of course, the unit vector pointing in the direction between p and p prime, is now, you know, this is a double sphere. So that's kind of interesting. And what we're interested in is extracting coarse-grained curvature at macroscopic, in general, scales delta. So why is that? My God, this is just terror. So, so we are interested. So we are looking at our quantum geometries. We have them in a computer, so they are built from hundreds of thousands of simplicial building blocks, and we're simulating the dynamics of these ensembles, and we are evaluating certain geometric observables in there, among them precisely this quantum Ricci curvature. So there is an initial regime where everything is dictated by what we call lattice artifacts. Just we have chosen, you know, to regularize our geometries with triangles, and this is just a choice, and it produces some curves that, yeah, the initial part of the deltas is just uninteresting physics, because we are only interested in a way in the n to infinitum limit. Then what we might be able to see for slightly larger delta is hopefully some kind of quantum effects. For sufficiently large delta, we hope to recover classical properties. And then when we go to really large delta, there are probably global effects, finite size effects. So there are all these regions we are interested to study as a function of delta. So the simplest thing is to take a geometry, sum over all point pairs p prime with given delta, and then, so summing over all directions. And what you then do, you get what we call a curvature profile. So, which is delta dependent, which really tells you what is this kind of this term, that's what you're interested in. What is that characteristically for your quantum spacetime as a function of delta? So I would advocate this as in principle, an observable you can study classically, but no one would have the idea of studying this classically. But now here I'm saying, look, you have to look at this for various classical spaces, because what we see in the quantum theory, we would like to compare, at least, in some large scale limits, to what is this quantity is in certain model spaces. This is precisely, this is the simplest observable I can come up with. Is really an integrated Ricci scalar. So the beauty of the thing is this stays finite in the n equal to infinity. So what we physicists call is a renormalized notion of curvature, and that's very, very important. I'm running out of time, and here's a picture. So what is the coarse graining about? Well, just imagine implementing this notion on a flat regular lattice. These are two spheres of radius 3 with linked distance, right? So this is one test case where we are testing our prescription. And what you see here is for small delta, you see the lattice discretization effect and basically the anisotropy of the lattice, which is these unphysical points here that become large here. So what we are seeing here is, this is of course a flat space, and our quantum Ricci curvature reproduces that by producing kind of flat curves for you. So the quotient is a constant for all delta. Yeah. So it functions beautifully, but you see large scales you cannot trust. And well, here this is also something one can compute in principle analytically. But so that's just a sanity check. Now the interesting thing is applying this in the quantum context. So if I apply it to a weird geometry like this, so there's text missing here, which says the measured expectation value for a typical geometry that comes out of two-dimensional Lorentzian quantum gravity, has a quantum Ricci curvature, a curvature profile as a function of delta, which looks like this here. So what is this? For different volumes of these quantum spacetimes, you are measuring the curvature. You see, for the smaller volumes, you see finite size effects from the fact that the two spheres will wrap around the compact direction. For larger and larger spacetimes, this effect is not there, and you see kind of what the true quantum Ricci curvature is. It doesn't seem to, it's unclear whether it becomes a flat curve. That would just mean it's a flat space, but it doesn't, we call it quantum flat. So there is a small inclination. Who knows how it will continue here. For the Euclidean quantum universe, this is what comes out of Liouville gravity. We are doing the same story, and we can map the measurements to the data for a round continuum sphere. So these very bizarre objects, if I measure their integrated quantum Ricci scalar, if you like, it can be mapped onto that of a continuum sphere. So yeah, so you see the scope of what you can do. And the next thing is truly, this is the last result I'm showing. It's a truly interesting case we started off with. We have a four-dimensional emergent universe in this quantum gravity approach. And its volume profile, its shape looks like that of a de Sitter space. What can we say about its curvature? And this is what we can say. We model, we simulate this on large systems of up to 1.2 million building blocks, and we measure this quotient, and you see that again lattice artifacts for small delta, but beyond that, well, we see a reasonable closeness to the data of a continuum fourth sphere. So it's at least compatible in this very averaged sense, our quantum universe, with, in the sense of expectation values, averages, with a four-dimensional de Sitter space, also with regard now to its curvature properties. So, and that brings me to the very last slide. So the framework here is that of random geometry, and it's an extensive framework. It's something, to answer to, there was a question posed. This is something that will be there for a while in 2 dimensions, but people are trying, from the math side, to push this into 3 dimensions. physics is jumping ahead because we need it in 4 dimensions. And I've shown you what can be extracted from this in terms of interesting and concrete and quantitative results, of course, involving numerical methods, like the emergence of this de Sitter type universe. Geometric observables are key to understanding what these quantities are. We don't have so many yet, and we have only kind of, in terms of local geometry, this quantum Ricci curvature is what we have now. And it seems a very, very powerful tool. And I have already given you some examples of what we can do with it. It's also the first geometric quantity that is in principle direction independent, although what I've shown you was there was always an integral over directions. But this is different. For example, what we're looking at, for instance, if you're putting in a mass line into your geometry, then you locally can distinguish curvature along and perpendicular to the mass line. So already there, the direction dependence will become interesting and important. So we can, so that's what we are looking at. So we can put the curvature into curvature correlators. Why is that interesting? Because we want to relate to early universe physics. So it's a long story, but it's a very concrete path forward. And I hope I've given you, a little glimpse of what it's all about, even though some of the graphs are missing. So thanks so much for your attention.